Alright, in this video we'll be going through what is current. Now, although that might seem obvious, I guarantee you there is some holes on your knowledge on what current is. Now, that doesn't really speak to how smart you are or how knowledgeable you are as a person, more so how trash NCEA is and how poorly NCEA is taught. Alright, so I'm going to teach you current from the bottom up so you have no gaps in your knowledge and you can ace the exam with as little effort as possible. Alright, so as you have probably been taught, current is the rate of flow of charge. Now, first things first, before we even talk about current, we need to talk about charge, because as we can see by this definition, current is related to charge. Alright, so charge. Alright, so the electrostatic force, which is a fundamental force in the universe, has been attributed to electric charge, which we can denote as symbol Q or capital Q, okay? Either one. Now, charge is a physical property of matter which causes all matter to both experience and exert a force when placed next to each other. And through experiments, we have found out that there are two types of charges. Alright, so there are two types of charges. The first type are like ones, okay? Like ones meaning like charges, okay? And these ones repel each other. And the second type is opposite ones, okay? And these ones attract each other. And this right here has allowed us to define positive and negative charge, okay? From this, we were able to develop a model for which we are able to describe the electrostatic force which is caused by charge, okay? And so the electrostatic force, which we can denote as our electrostatic force, is directly proportional to Q1, Q2, all over R. Now, just a note, you don't need this specific formula for NCEA. Again, just some background knowledge for yourself. Okay, so as it's directly proportional, we can add a constant, which we can call Coulomb's constant, okay? And that we can denote as Ke, see? That's Coulomb's constant, okay? And so therefore, our electrostatic force is equal to our Coulomb's constant multiplied by Q1 times Q2 all over R, okay? And Q1 is the magnitude of our first charge, okay? And Q2 is the magnitude of our second charge. And R is the distance between the two charges. Again, you don't need to know this for NCEA level 3, so if you're just watching this like a few days before the exam and you're panicking, don't worry, you don't need this knowledge. But what it will do is help you understand what's happening, okay? So just know that there is a force that is pushing charges away and towards each other, okay? And this is our electrostatic force, all right? So how have we been able to harness this energy of charges? Well, like I said over here, we can see that opposite charges attract, okay? And so if we think about it, if the natural state of opposite charges is to come together, if we were to separate those opposite charges, then we would have potential energy. A way in which you can intuitively think about this is if you have a rubber band, okay? A rubber band will usually form a circle or like an oval, right, when it's unstretched. And the more you stretch it, the harder and harder it becomes to stretch. And you know from mechanics that the more you stretch a rubber band, the more elastic potential energy you're gaining. So it's kind of a similar idea. The more we separate charges, the more EP we gain. And when we separate opposite charges, those opposite charges gain energy. And what we can do is transport those opposite charges into electrical devices through conducting materials, and therefore make use of that energy. And as you might have guessed, that is kind of what a battery does. We would have a battery over here, okay? And let's say we have some positive charge up top, and also there's some negative charge here in amongst the positive charge, okay? Now, in this case, we have two opposite charges, and they like to be together. They attract each other, okay? And so the first thing that happens is, one, work is done by the battery in order to separate these charges, okay? And so what that will look like is our electrons moving to the other side, okay? We are creating distance. We are separating the charges. And so that is this process right here. And so the second part is the electrons, which we can denote as an E with a minus on it, okay? So this means electrons, okay? So electron gains energy, and it wants to return to its neutral state. And so what I mean by neutral state is that the electrons want to shoot back up as they are attracted to the positive charges, okay? And so that is this part right here, okay? And let's imagine this battery is connected to some sort of device, electrical device, on both ends. Sweet. So even though the electrons want to move back up, they can't because of the chemical reactions within the battery, okay? That's more for a chemistry class rather than a physics class, okay? What this pathway does through the device, it allows the electrons to have an alternative path through the device to be back united with the positive charge once more. So therefore, the third point is that conducting materials allow alternative path for electrons to go back to neutral state, okay? And then in here, work is done by the electrons, thus transferring their energy that they gained from being separated by their positive charge, okay? All right, work done by the electrons, thus transferring energy to the device. And therefore, when the electrons come through here, lastly, they return to their neutral state. And then when all the electrons are back to their neutral state, the battery is then depleted, and therefore you need to charge the battery again, which is again another chemical process, which will force the electrons back down again, okay? And therefore your battery is now charged, and so now you can use that energy, which you gained from separating the electrons. Again, you do not need to know this for NCEA level 3, just some knowledge for you so you know what's actually happening in a circuit. And you're not just memorizing the answers that you memorized from doing past papers, okay? And re-practicing the same questions over and over again. If you're doing that way of learning, then best believe that way of learning is going to bite you in the ass when you finally go to university, if you even are going to university, which I assume you are if you're doing physics. It's not really a dropout subject, is it? So what I'm saying is, I highly recommend actually learning what's happening, not just rote memorizing the answers. So carrying on. So now we know what charge is and how it relates to our circuit, okay? We can now move on to current. All right? Current, which uses the symbol lowercase I or uppercase I, okay? I'm pretty sure uppercase I is the most common in NCEA. And like I said at the start of the video, current is the amount of charge passing through a singular point at a single second, okay? In other words, it measures the rate of flow of electrical charge, okay? And so mathematically speaking, if this is the rate of flow of electrical charge, then we can denote this mathematically as the derivative of the total number of charges passing a given section of a circuit over a period of time. So we can write that as I is equal to dq all over dt. Now remember, our q is our charge, and our t is obviously our time, and we should know the notation for derivative from our math courses, okay? Now if we think about this, does this make sense? Okay, if we were to graph this, if we were to graph the number of charge, and this is over a period of time, okay? And this is the amount of charge flowing through a given component, let's say. And let's say it looks something like this, okay? We should know from our math courses that the derivative is the rate of change. And like I said in the beginning, current is the amount of charge flowing through a component over a given time. And so if we have charge on our y-axis and time on our x-axis, this is obviously going to be the gradient of our graph, okay? And we should know from our math courses that our derivative is our gradient. And so therefore, if we take our derivative of our charge all over our time, we get our current, okay? So charge has the unit of coulombs. So the unit for charge is C, which is coulombs, okay? So if charge has the unit of coulombs, and our current is the amount of coulombs over time, and obviously we know that time has the unit of seconds, we can say that current has the units coulombs s to the minus 1, okay? And so this will be said in English as coulombs per second. But as you know, commonly we just use A, which stands for ampere, okay? Now, why do we care about current more than we care about charge? Okay, I'm assuming in your NCEA journey that you've learned very, very little about charge and mostly about current. This is because in order for an electrical device to work, we need a continuous flow of electrons to flow through it, okay? A continuous flow of charge. And therefore, we do not care about the total number of charge that is flowing through the device. We just care about if charge is flowing or not, which is current. Because if charge is flowing, that means that the device is working and should be on. Also, the rate of current tells us how fast the device is absorbing energy, right? And so if a device is pulling a high amount of current, we can say that that device is using up a large amount of energy. Because as we said, each electron that passes through the device transfers energy to the device from the potential energy it gained from being separated by the positive charge. All right, so once again, along your NCEA journey, you have probably come across the idea of conventional current, and you have probably heard somewhere that conventional current is wrong, which that would be correct. Conventional current is wrong. This is because, as I stated up here, we know that the charge that flows through our electrical circuit is actually electrons, which we denote as negative charge. However, conventional current describes the positive charge that flows through the circuit, okay? Now you might be wondering, after all these years of knowing that conventional current is wrong, why have we not changed it? Well, that's because conventional current is just the opposite of electron flow, okay? And so this could be just thought of as a lack of an electron. And so this really had no impact on how devices or theories were formed, but the results and the numbers and the experiments all remained the same, so there was no real need to change something that was well established, okay? That's the only reason why we continuously do something that's incorrect. We denote conventional current using arrows along the wire of a circuit, okay, like so. And we can say that this is some arbitrary current. Alright, so that is it for this video on the fundamentals of current.